A balanced counterflow heat exchanger has a surface area of 20 meter square and overall heat transfer coefficient of 20 watt per meter square Kelvin. Air whose specific heat capacity at constant pressure is 1000 joule per kg Kelvin entering at 0.4 kg per second and 280 Kelvin is to be preheated by the air leaving the system at 0.4 kilogram per second and 300 Kelvin. The outlet temperature in Kelvin of the preheated air is, so let's see the counterflow heat exchanger here. So this diagram represents that the hot fluid enters from this section, let's say this is 1 and 2, and exit here at 2, and in the counterclockwise direction the cold fluid enters. So this is inlet of cold fluid TCI, the temperature at the inlet of cold fluid, and this is the temperature at the exit of the cold fluid. Okay, so Q, the heat transfer, is equal to the overall heat transfer coefficient multiplied by the area, the surface area of heat exchanger, multiplied by theta m, which is the mean temperature difference, and this is equal to Cp of hot fluid, plus that Cph, into Thi minus Th naught, or the exit temperature of hot fluid at the exit, which is also equal to Cp of the cold fluid, heat capacity of the cold fluid, multiplied by T, the temperature of cold fluid at the exit, minus temperature of cold fluid at the entry. Okay, now according to the problem, Cph is equal to Cp of cold fluid, which will be equal to mass flow rate, that is 0.4 times the heat capacity, which is 1000. So this will be equal to 400 joule per Kelvin. Okay, now we have got the value of Cp. Area in the problem is 20 meter square and the overall heat transfer coefficient is 20 watt per meter square Kelvin. Also TCI, it's given in the problem, TCI is equal to 280 Kelvin. Temperature of cold fluid at the entry, temperature of hot fluid at the exit is 300 Kelvin. For same heat capacity of hot and cold fluid, to delta T1, which is equal to delta T2, which is equal to Th naught, or at the exit, minus T, temperature of the cold fluid at the entry. So this will be equal to 300 minus 280, which is 20. Okay, now we have got the value of theta m as well. Now we'll just substitute all the value here in this equation. We can write U is 20, area is also 20, theta m that we have got is again 20, is equal to Cph is equal to Cpc, that is 400 multiplied by the temperature of cold fluid at the exit minus the temperature of cold fluid at the entry, so that is 280. And from here we can calculate, this will be, this we can cancel out, this will be cancelled out, so Tc naught will be equal to 280 plus 20, which is 300 Kelvin. So temperature of cold fluid at the exit of the heat exchanger, when it exits the heat exchanger, will be 300 Kelvin. Okay, so the correct option is option B. For more on heat exchangers, you can refer to the NPTEL course, lecture number 25, Heat Exchangers 1, a lecture series on heat and mass transfer by Professor S.P. Sukhatme and Professor U.N. Gaitonde of the Department of Mechanical Engineering at IIT Bombay.